Okay, I'm not late. I've still got 8 seconds. Let's see. Turn that thing on. Okay. I think we're ready to go. I've posted a new homework assignment, sort of. Hang on a sec. I put just the Word document for the homework assignment is in the example problems folder for this week. And I still have to come up with a 4th question on it, one of the conceptual questions. So it's almost complete other than that. And I also posted the material for the resistivity lab finally. And so that is up there, and that'll be due in a week. And other things. That's about all I can think of off the top of my head. Yesterday was a crazy day. People go until 9 o'clock at night, or a little ways past there. So, however, today we'll continue on with looking at magnetism stuff. And I wanted to show you something about dealing with the cross product that may help a little bit. Not everyone has used a determinant yet. And so I wanted to just show you something that you can do with that. So we'll switch over to the visualizer here, and hopefully it'll work. Or maybe I'll just switch the screen to, that should be better. Okay, this may not be in focus yet. Better give it something to focus on. And yeah, that ought to work. Okay. The other day, we found out that the force that a magnetic field exerts on a moving charge is given by F equals QV cross B. And not everybody has ever dealt with the cross product before, so I wanted to show you how that might work out. And let's just take a couple of vectors, A, which is going to be AX along I hat, plus AYJ hat, plus, I may just give it 2 components, just for the heck of it, to keep this simple, because it'll be more similar to the what you need on a homework problem. And then B can be BY along J hat plus BZ along K hat. So this vector will lie in the XY plane. This vector will lie in the BZ plane, or the YZ plane. And so if you imagine those things, what they look like, often we have them oriented this way. So X, Y, and Z. And just to help, I hat points that way, J hat points that way, and K hat points that way. Okay, now if we imagine the cross product of these 2 vectors, there are some properties that we can deal with that are like the distribution property and mostly the distributive property, I think. But A cross B will equal AX along I hat plus AY along J hat crossed with BY along J hat plus BZ along K hat. Okay, and then I'm going to split this into two parts where I write it like this. First, I'll just take this crossed with that. So I'll have AX along I hat crossed with BY along J hat plus BZ along K hat plus AY along J hat plus, whoops, crossed with BY along J hat plus BZ along K hat. Okay, so what I did was I split this into two. And then I'll do it again. Then I'll split this into two. So I'll have AX along I hat crossed with this plus AX along I hat crossed with this. And so let's see, AX along I hat crossed with BY along J hat plus AX along I hat crossed with BZ along K hat, and do the same thing with these last two terms down here, plus AY along J hat crossed with BY along J hat. I think I got all my hats on there, plus AY along J hat crossed with BZ along K hat. So I actually split this cross product into four terms. If I'd had all three dimensions for each of these vectors, I'd be ending up with 9 terms. But they're not all going to be non-zero. For instance, J hat cross J hat here. Remember the magnitude of the cross product, A cross B, is equal to the magnitude of A, the magnitude of B, times the sine of the angle between them. Okay. If you take two things that both point in the J hat direction, the vector part of this, you can factor out the scalar parts, but the vector part will be J hat cross J hat, and a vector crossed with itself or with the negative of itself is 0, because the sine of 0 is 0 and the sine of 180 degrees is 0. And so this ends up being 0. And then for the other things, let's learn something about cross products of unit vectors. I hat cross J hat. Okay, imagine pointing the fingers of your right hand in the direction of I hat so that they can curl toward J hat, and you get K hat is what you get. Okay. Now, J hat cross I hat is equal to, well, then you take fingers of your right hand, point them in the direction, maybe I should draw a huge one here, a huge XY coordinate system so you can kind of imagine this a little better. And try this for yourself too. Just draw them to convince yourself of this. This is supposed to be a representation of a three-dimensional coordinate system. So here's X, here's Y, and here's Z going up like that. So I hat points this way, J hat points that way, and K hat points that way. So J hat cross I hat, okay, J hat crossed into I hat will equal minus K hat. So I hat cross J hat was K hat, J hat cross I hat is minus K hat. And then I guess we could figure out all of them. We already took care of this pair. So what about I hat cross K hat? Okay, well, I hat, point your fingers that way so you can curl them toward the K hat, and it'll be negative J hat. And then try K hat cross I hat. Okay, point the fingers toward K hat so you can curl them toward I hat, and they'll point in the J hat direction. So, and actually, I mentioned the other day that the cross product was anti-commutative, where you do it in reverse order and you get the negative of it. So there's something that happens. And then let's see, what have we got left? J hat and K hat. J hat cross K hat. J hat cross K hat. This is kind of hard to do, but it'll point in the I hat direction. And I'm pretty sure that K hat cross J hat, K hat cross J hat will point in the minus I hat direction. So there, those are some things that'll help. So this I hat cross J hat term here, I hat cross J hat, that'll point in the K hat direction. And it doesn't hurt every time you do one of these things to not try to memorize it, but try to figure it out on here. So this will point in the K hat direction. I hat cross K hat, I hat cross K hat, that'll be in the negative J hat direction. And then J hat cross K hat, J hat cross K hat, that'll point in the I hat direction. So you'll end up with all three coordinates for this cross product, but it's doable anyway. And the AX and BY will just be whatever the components of those things happen to be. It may be that one or the other of them is negative, and so you might have to imagine a minus I hat term and a minus J hat, and you can figure out what all of those cross products will be too with each of the other ones. So things that you can do, and try to familiarize yourself with that right-hand rule. You might want to do a little bit of research, maybe in your textbook, maybe in other textbooks, on the right-hand rule for cross products, and see if you can start getting a feel for it, for the way that it works. So let's jump back to some of the other problems that we were looking at the other day. Whoops, those are the wrong ones. Got them in. Yeah, I think we'll start with this one today. Show that the radius of curvature of a proton moving at a velocity of 25 meters per or kilometers per second in a magnetic field of 10 to the minus 10th Tesla is small compared to interplanetary distances. By the way, something I didn't talk about the other day was the path of a charged particle in a magnetic field. We'd sort of been looking at situations where the velocity was parallel or anti-parallel to the magnetic field, in which case there's no force on it. And then we looked at the situation where it was perpendicular, but what if it's somewhere between perpendicular and parallel to that magnetic field, which is going to be the more general case. And what you have in that case is something that you actually saw in one of the demonstrations that I did the other day. But, oh boy, how to picture this. Let's suppose that the particle velocity is in this direction, but the magnetic field is maybe in a direction like that. So they're neither perpendicular nor parallel. And actually, we can draw that. So let's suppose V is that way and B is that way. Well, you can split the velocity, and actually any two vectors determine a plane, so that'll always be the case. All right, well, it's only this. You can split the velocity into a part that is along the magnetic field. So I can call this V sub parallel, if that looks like a parallel symbol. And then this will be V perpendicular, that part of the velocity that's perpendicular to the magnetic field. And for the parallel component, remember it's QV cross B, this would split into QV parallel cross B plus QV perpendicular cross B, because V itself is this vector sum of those two things. Well, this is going to be 0, and that's because the magnitude of a cross product is the magnitude of one vector, the magnitude of the other vector, and the sine of the angle between them. And if it's parallel, that angle will either be 0 or 180 degrees if it happens to be anti-parallel. And so we don't even have to think about that. But this velocity will not be changed. That component of the velocity won't be changed. And so it will continue moving either parallel or anti-parallel to the magnetic field. This is the one that will end up being changed, and we'll have a force that's always perpendicular to that component of the velocity, which means if that velocity is pointing out up here, the force on it will be perpendicular to the plane of these two things. But that's only at an instant. It'll change in that instant, and then the force will be perpendicular to its new plane of B and B. And this term ends up giving you circular motion, while this term ends up giving you non-circular motion. And what you end up with is a, whoops, can't draw on two things at once, is a helix going into space, where it's got a circular part to it and a non-circular part to it. And you actually saw that in one of the demonstrations when I brought that great big magnet up there. For a little bit, you saw the electrons doing something like that in there. And that's the more general behavior of a charged particle in a magnetic field. However, in this case, we're not quite going that far. We're just interested in maybe the perpendicular case here. So radius of curvature of a proton moving that fast in a magnetic field. Well, this is just going to be F equals QVB, and that would be the maximum force. That would be the sine of 90 degrees out here, which is 1. And that will equal MA, but in the case where they're perpendicular, the acceleration will be that for centripetal motion. So this will be mv squared over r. And we did an example like this the other day. But let's go ahead and figure out the radius of curvature here. So setting these two equal to each other, QVB equals mv squared over r. Solve for r, and we'll get mv over qb. One of the v's divides out. So it's a proton we're talking about here. 1.67 times 10 to the minus 19th kilogram, wait a sec, 10 to the minus 27th kilograms. The speed of it, 25 times 10 to the third meters per second. And then Q is, this is the one with the 10 to the minus 19th, 1.60 times 10 to the minus 19th coulombs. And the magnetic field, 10 to the minus 10th Tesla. So we're really after an order of magnitude here. 1 times 10 to the minus 10th Now remember, a Tesla is a Newton per amp meter, but an amp is a Coulomb per second, so we could think of this as a Newton per Coulomb per second meter. And I'm going to do that. Newton per, whoops. Yeah, it is. It's a Newton over a Coulomb, a Newton second per Coulomb meter. Yeah, that'll work. Let's see, and the coulombs divide out. Let's see. This will come up top. A second per meter will multiply and give me meters squared per second squared. And a kilogram meter squared per second squared is a joule or a Newton meter. And I'll end up with meters. Okay, trust me, or figure that out for yourself. So Newton meters on top, newtons were left on the bottom, so I end up with meters for that radius of curvature. And since we're only after an order of magnitude here, well, I better plug it in. This part is approximately 1, but we'll see. Divided by... And I get about roughly 3 times 10 to the 6th meters. Okay, that is actually small compared to interplanetary distances, especially because the radius of the Earth is, to one significant figure, is 6 times 10 to the 6th meters. And that's just the radius of the Earth. And so this is actually less than the radius of the Earth. And so the distance out to the moon is, oh, what is it? 400,000 kilometers, which is about 4 times 10 to the 8th meters. So whoops, capitalize moon when you're talking about our moon. So anyway, this is a lot bigger than this radius of curvature, more than 100 times larger. So yeah, that's the way they behave. Now, we haven't really talked about shapes of magnetic fields or anything else yet, but the Earth's magnetic field at the current time is roughly equal to the magnetic field of a bar magnet. Here's what the magnetic field of a bar magnet looks like. It's got a north pole and a south pole, and if you were to map out that thing, it'd be symmetric either side, but it looks about like that. And that's about what the Earth's magnetic field looks like at the current time. That's not always the shape of the Earth's magnetic field. Over geologic time, it has changed considerably. And there have been times when it was pretty darn chaotic, and it also reverses direction occasionally. An interesting thing about the Earth's magnetic field is that the north magnetic field of the Earth is actually the south pole of a magnet. Remember that opposites attract parts? The north end of a compass will point to the north magnetic pole of the Earth, because the north magnetic pole of the Earth is actually a south magnetic pole. It's enough to drive you crazy. However, going back to the Earth here, we've got a north pole and a south pole, and these are the line through the north and south pole is the rotational axis of the Earth, but the magnetic field doesn't line up with that. If you've ever done backpacking and used a compass for anything, you'll find out that it's off from that. So here's our little bar magnet inside the Earth. It's actually currents in the outer core of the Earth, convection currents that have to do with the magnetic field. But I'm not sticking arrows on here on these, but that's the what the Earth's magnetic field looks like going out into space roughly, and it should be nice and symmetric and everything. But the sun puts out this constant stream of charged particles, mostly protons and electrons. It's called the solar wind, but there's also other stuff mixed in there. There's helium, and between protons and electrons and helium, that accounts for almost all of it, but there's also other stuff occasionally. The sun has trace amounts of more massive elements. But anyway, when those things come into the Earth, they'll be whooshing along here, and they will, I guess the Earth turns on its axis once a day. So this thing kind of, imagine the rotation of this as the rotation of this thing along these lines occurs. But they'll get caught up in these Earth's magnetic field lines, these charged particles from the sun, and they'll spiral along them and come down here and hit like that. And some of them will spiral along the ones down here and hit the Earth like that. And they hit in kind of the upper atmosphere, several tens of kilometers high. And when they smack into mostly the nitrogen atoms in the upper atmosphere, because that's most of the Earth's atmosphere, the nitrogen atoms will give off light. And that's what causes the aurora. Every once in a while, the sun puts out stronger blasts of material. They call those coronal mass ejections. And if one of those happens to be headed toward the Earth, then we get more spectacular aurora borealis up here and aurora australis down here in the southern hemisphere. And stuff like that happens. Every once in a while, there are even more severe storms that happen when there's big blasts of stuff coming from the sun. There was one in the 1800s, mid 1800s, and I forget the date of it, but it was a time when pretty much the quickest way to send a signal to anyone was through telegraph. And a telegraph was a wire that ran between towns and cities and stuff. And it was kept charged, and people would do Morse code. They just send out a signal of dots and dashes along the thing. But anyway, you had these long wires running between places. And in this storm that happened in the mid 1800s, this geomagnetic storm, you could think of it, although it was the sun's fault, but it induced currents in those wires, and a lot of telegraph operators were shocked. They shut their things down, and they found they were still having current carried in the wires. And it was just sort of, I guess it was, I mainly read about it in the US, but there were other countries that have them as well. And kind of crazy to have things like that happen. There hasn't been anything that severe since then. Although there was a time back in the, I think it was in the 1970s, there was something similar to that. And there were places up in northern Canada where they had power lines that ran from dams down to the cities that were farther south in Canada. And the power lines were hundreds of miles long. And this particular solar geomagnetic storm induced a lot of currents in those and knocked out power lines and stuff. And since then, they've tried to have means of preventing those large currents from being induced. But I don't know that we've had anything quite that severe since then. Northern lights are kind of neat to see. They're usually kind of pale. a lot of times when I've seen them, I'd be looking at them and thinking, am I seeing things? One time we were out stargazing with my astronomy class, and I saw this glow to the north, and I thought, well, that's weird. Soap Lake usually doesn't have that bright a sky glow. And then I realized it was northern lights that we were seeing. And so that was kind of a weird thing to have happen. But it's magnetism, and it's charged particles moving in magnetic fields that cause those northern lights. So it's kind of neat that way. Let's see. Okay, there are a region of space around the Earth called the Van Allen belts, Van Allen, and the average radius of curvature of the trajectory of electrons in there is 300 meters, and their average electron energy is 100 kilo electron volts. What's the value of the Earth's magnetic field in that region? Well, we're going to have to do some work to figure this out. The electron energy, though, that's going to be their kinetic energy. So we'll have 1/2 mv squared for those electrons is going to equal 100 times 10 to the third electron volts. And I'll multiply that by 1.602 or 1.60 times 10 to the minus 19th joules per electron volt. And that way I can convert it into joules. I'm after figuring out the speed of the electrons here. So whatever that turns in, oh, that should be easy. This is 1 times 10 to the 5th. So it'll be 1.6 times 10 to the minus 14th joules. And I'm assuming I'm keeping 2 significant figures just to have this thing be more interesting. But with what we're given, we've really only got 1. So we'll knock it down to 1 sig fig when we're all the way done. Then the speed of the electrons is going to equal 2 times that, or the square root of 2 times 1.6 times 10 to the minus 14th joules divided by the mass of the electron, which is 9.11 times 10 to the minus 31 kilograms. And a joule is a kilogram meter squared per second squared. The kilograms will go away and I'll end up with meters per second for the speed here. So lots of stuff. That's 3.2. And I have to take the square root of that. These things are going at a pretty good clip. About 2 times 10 to the 8th meters per second. Okay, we should be using relativistic dynamics for this, but because that's 2/3 of the speed of light, that's up to where that would matter. But yeah, that's pretty fast, but we don't have the means for that yet. So let's try and figure out, that's the V, and we'll have that if we assume the perpendicular angle between the velocities and the magnetic field, it's about all we can do because we're not told what that angle might be. But QVB, this would be the maximum force, is going to equal the force that's acting on the electrons, which is MA, which is MV squared over R. Oh, I guess I could have saved myself some trouble here. Yeah, the MV squared is going to be 3.2 times 10 to the minus 14th joules. I'll just do that. No, I did want to know that speed because it shows up over here too. So, well, that won't hurt. Anyway, 3.2 times 10 to the minus 14th joules over the radius of these things, which is 300 meters. And that will equal the charge on the electron. We're just after the magnetic field, but that will equal 1.6 times 10 to the minus 19th coulombs times, oh man, all sorts of stuff would have divided out here if I'd been smarter. 2 times 10 to the 8th meters per second times B will equal this particular division here, which is this is about close enough here for what we've got. 1 times 10 to the minus 16th joules per meter, which is just a weird combination, but that's all right. So B will equal 1 times 10 to the minus 16th joules per meter divided by 1.6 times 10 to the minus 19th coulombs times 2 times 10 to the 8th meters per second. Oh, a joule per meter. A joule is a Newton meter. This is just a Newton on top. On the bottom, we have coulomb meters per second, or coulombs per second times meters, or amp meters. This is a Newton per amp meter. That's good. That's a Tesla. So that's what we'll end up with. So divided by 1.6 E minus 19 times 2 times 10 to the 8th. And I think I've got parentheses where I need them. And I get about 3 times 10 to the minus 6th Tesla. So the magnetic field gets weaker as you get it farther away from the Earth. And so there, that's about what it is up there. So all sorts of different examples that you can do for things. I may save this one. I wanted to start something else today. And that was to start looking at magnetic forces on currents. And we haven't really studied currents much. Maybe we've measured them a little bit, or maybe we haven't. But anyway, we'll imagine a cylindrical wire, and in this wire we'll have charge carriers, and we know that it's really electrons doing the charge carrying, but we can, yeah, let's go ahead and think of little E minuses in here that are the charge carriers. And so they're going along here like this, and moving with some particular speed. And on average, they'll have a velocity which is going to be v sub d is the way it's often written, and that's called the drift velocity of the electrons. The electrons move in response to an electric field that's been put in the wire, and you do that by having a potential difference between the opposite ends of the wire. You can make a positive potential difference here and a negative potential difference here, or a negative positive potential here, negative potential here, and that will make an electric field in the wire that points from positive to negative, but electrons go opposite that electric field, and so they'll have a drift velocity in some direction. Okay, now the electric current I mentioned this yesterday. It's the charge per unit time that will flow past some particular point in the wire. And it'll be about the same everywhere in the wire. You don't have places where charges are building up, and you don't have places where charges are diminishing. It pretty much stays the same all the time. And that electric current is the charge per unit time that's going through the wire. And we measure electric currents in coulombs per second. Those are our units of charge. Well, how many coulombs per second will go along here? See if we can figure that out. We're going to need some more things, basically. One thing we'll need is a number for the charge carriers per unit volume. So and then we'll imagine some little slice of the wire, and this will have a width of it that will let be V sub D delta T. And this will be the volume of space in which the all of the charges will go from either within this volume or on the left end of the volume through some little slice of it in a unit time. And so we'll catch all the charges in there. Well, within charge carriers per unit volume, the volume of this would equal this length times the cross-sectional area of the wire. And we'll just call that A. And so we'll have the volume A times V sub D delta T. That will be the volume there. And if I multiply that by N, that's the number of charge carriers that will pass through that some little slice of this per unit time, or in the time delta T. So passing, and that should be the same everywhere in the wire, although we picked a particular time interval here, but we'll fix that. Passing through right end of volume in delta T. Well, how much charge will that be? Well, we know what the charge is on electrons, but let's just go ahead and call it Q. So it'll be Q in A V sub D delta T is going to be the amount of charge in delta T. And if I divide that by delta T, I'll have the current. So that will be the current. Except, let's see, A V sub D. This will be volume per second. I've got too many delta T's here, I think. No, that should be okay. Should be NQV sub D is what I'm after, I think. It might have an A in there. I can't remember. Oh, guess if I look at the first page of my notes, I might have it there. Yeah, that's right. So I am okay. Yeah, current is equal to NQ V sub D times A. So we're good to go there. Something that's sometimes dealt with is the current density. And if you divide by A, you get the current density, although I don't know that we're ever going to use that. But this is an idea of the electric current that's traveling through a wire at any given instant. And I mentioned at some point that the actual drift velocities or the charges are not going particularly fast. It may have been 2 days ago that I mentioned that it's on the order of centimeters per hour and things like that. And the reason that they don't have to go very fast is this number is sky high. In a conductor like copper or aluminum or silver or things like that, there are on the order of 1 free electron per atom. And so the number of charge carriers per unit volume is roughly equivalent to the number of atoms per unit volume, which is really high. And so it's this number being extremely high that can generate a fair amount of current, even though this number ends up being pretty small. And then the charge on each one of these things is pretty small as well. So, but it's the N being very high that allows, you've already got a small number here, and the cross-sectional area of the wire is generally pretty small, but the drift velocity ends up being surprisingly small as well. In fact, let's go ahead and calculate one just for the heck of it. And then tomorrow we're going to look at how with all of these charges in the wire having roughly, well, this drift velocity is the average velocity of them. Each one of those will be thought of as a moving charge in a magnetic field. And if you've got this electric current in a magnetic field, there will be a magnetic force on that due to QV cross B, but for every one of the little charges in here. And so individually, they may not be that big. Let me look up the file for your lab and just pick a wire and figure out the drift velocity in there. Let's see, labs. Measuring, there we go, measuring resistivity. That's the one. And I'll drag this over here so you can see it. This is part of the lab that you're doing that I just posted today. But this shows for different gauges of wire what the diameter in millimeters of the wire might be. And so we'll use that to figure out the drift velocity. And let's just pick a 12 gauge wire, which might be a somewhat heavy wire for home use, but it could be, this is something that I think tends to be more modern. They used to stick thinner wire in houses, and now we have more electrical devices. So let's pick a 12 gauge wire, which has a diameter of 2.05 millimeters, and go from that. So then I'll save a little spot here to solve this problem. You
need to move the Word document out of the way.
Yeah, I'll move it out of the way. I wanted to copy that number down first. Oh, rats. Alt-F-C. There, get that out of there. Okay, so we've got a wire with a diameter of 2.05 millimeters, that'll make the area is going to be pi times the diameter squared over 4. So it'll be pi times 2.05 times 10 to the minus 3 meters squared divided by 4. And actually, that'll end up being about 4 times 10 to the minus 6th. 4 over 4 is 1. So this cross-sectional area will be approximately pi times 10 to the minus 6th, or let's just call it 3 times 10 to the minus 6th meters squared. And let's suppose that this wire, this will be I equals NQ V sub D times A. Oh, I'm going to need one other number, and that is the density of copper. And if somebody's got a handy access, otherwise I'll just call it up on Wikipedia and figure it out. But we now know the A, we're after the V sub D, so let's let the current be just 3.0 amperes, which is 3.0 coulombs per second. So the drift velocity will equal I divided by NQA, and 3.0 times, well, not times anything, coulombs per second divided by, now this N is going to be the one that's a challenge, but I can figure it out from the density of copper. And I'm just going with atoms per unit volume. I don't know, it may be in copper that you have on average 2 electrons per atom, but we'll just go with one of these and just get a feel for this. And so I'll need the density of copper to start with. And that shouldn't be hard to find. Go to Wikipedia here, something new. And look up copper. Density, near room temperature, 8.96 grams per cubic centimeter, which actually ends up being 8.96 kilograms per cubic meter. And then times, let's see, the molar mass, wherever it is. Atomic number, standard atomic weight. Okay, that's approximately that. Let's just pick 64 grams per mole. Or 1 mole over 64 times 10 to the minus 3rd kilograms. So that'll get rid of kilograms, times 6.02 times 10 to the 23rd atoms per mole.
We can't see the paper.
Whoops. Okay.
It's still away.
Now we're back. Okay. What have we got here first? The kilograms will go away. The moles will go away, and I'll end up with atoms per cubic meter. And I'm just going to go with that as my approximation. And it'll be a fairly large number here. It'll equal 8.96 times, whoops, this is times 10 to the 3rd. It was grams per cubic centimeter, but when you convert that to kilograms per cubic meter, you end up picking up a 10 to the 3rd on there. Let's see, EE. 3. And I get a fairly large number of 8.4 times 10 to the 28th atoms per meter cubed. Okay, so that'll go down here. 8.4 times 10 to the 28th. And really the only units on here are meters to the -3. And Q is 1.60 times 10 to the -19th coulombs. And the cross-sectional area, I forgot, 3 times 10 to the 6 meters squared.
So 3 to the -6.
Oh, -6, yes. Okay, so let's see, unit-wise, meters squared on this, meter to the -1 on that. Oh, and I should end up with meters per second. Okay, these coulombs go with that. I'll have meters left on top. Meters per second is what I'll end up with. Well, that's good. Okay, so finally, try this out. 3 divided by that last calculations result, second answer, times A, 3 times 10 to the -6th. And let's hope I didn't foul anything up. I get a pretty small drift velocity here of about 7 times 10 to the -5th meters per second. And if you multiply that by 3,600 seconds in an hour, you get about 27 centimeters per hour. So that's a little higher than I thought it was, although I think there may be more than one charge carrier per atom in copper, which would knock this down by a little bit. But that's not very fast. 27 centimeters is this far, okay? It's about roughly 11 inches, and that's in an hour. So those electrons are not going very fast on average. But we'll stop there today, and tomorrow move on from this and look at magnetic forces on currents, and then maybe some other things related to that, like torques on current loops and things like that. Again, there's a homework posted, and the resistivity lab is posted as well. So you can go on from there. Any questions? Okay, I'll stop the share and get ready for the next round. So I'll talk to you all tomorrow probably.